Okay, so now let's look at the time complexity of this. Okay, even though that this is a simple example, but this does help to introduce the so-called recurrence relations, and also in general, how do we solve a recurrence relation? Okay, let's look at the algorithm again. So here it is, and this is a recursive algorithm. Okay, all right. Now, let's look at this and first ask ourselves that what is the best case of this algorithm? Okay. Well, the worst case takes some time to analyze, but the best case in this for this algorithm is actually simple, because if we get lucky, okay, either you return here, here, or you check the middle, and the middle happen to be the number you're looking for, then we immediately return. We don't need to go, we will not go to any of this recursive calls, okay? So if we're lucky, if the number you're looking for is in the middle of the current array, then we return in constant time. So the best case, no matter how big your input size is, okay, if you get lucky, then it's only constant time for this one. So that's easy, okay? All right, let's now look at the worst case, okay? In general, when we have a piece of code, how do we analyze the time complexity? Essentially, you just look at line by line, command line by command line, ask how much time does this step takes, okay? So we look at this algorithm, and this part takes constant time, okay? And this too also takes constant time, okay? However, now this is the issue, okay? Number one, we now have two cases. I don't know whether I'm going to go to this case or whether I'm going to go to this case. What the algorithm would take during the runtime, that depends on what is your target you're looking for, right? But I know that I would either go to this choice, choice A, or I go to choice B. That's issue number one, okay? What's the issue number two? Well, I have this command line. So the time complexity is that I just add up the cost of each command line. But what is the cost of this command line? I don't know, because it's a recursive call. I'm calling yet another function. Okay, so how do we figure out what is the time for this one? Similarly, what is the time for this command line? Okay, so here is how we think about the problem. Okay, let's say that I'm going to use, for the worst case, I'm going to use T of n to represent the worst case time complexity for this algorithm when the size of input subarray we inspect is n. Okay, so remember we have an array, but we only inspect the array within a portion. Okay, so let's say that T of n to represent when that portion has size m. This is the running time of the algorithm. Okay, so that's the meaning of this. And as we said, what we do is that we do it line by line. I said that T of n equal to, all right, first I have to go through this part that takes at most C1 time. Then I have to go through this part that takes at most C2 time. Now, I would either go here or I go here. Okay, but I don't know which part I'm going to. Okay, however, we are looking at worst case time complexity. Okay, so I know it's either this or this. What is the worst case? The worst case is the one that takes more time. In other words, I'm going to look at the maximum of, so call this line star and this line star star. Okay, time for, in fact, let me write it here so that I can write it out. I hope it on the screen can still see. T of n equal to C1 plus C2. Then I need to look at which of these two takes a bigger time. So the maximum of time for star or time for star star. This is how you handle if condition. When you have cases, since we care about the worst case time complexity, you look at all the cases, you say which one is the worst, which one takes most time, and then you add that one. Okay, so that's how to resolve issue number 1. Issue number 2, what is the time it takes for the line star or line star star? Well, these are recursive calls. Okay, so if this is for this line, for example, I have to call the same algorithm on this array, but then only on the left half, which means that if the original size is n, then for this new recursive call, the problem size now become n over 2 because I only look at half of it. Okay, so that means that this part is bounded by t of n over 2. Okay, I'm skipping all the floors. You can think that this is a smaller than at most because depends because we have the floor here. So it's either n over 2 or n over 2 minus 1, but then that's bounded by this. Okay, same for this step. I know that now I'm calling the same algorithm on the right half. That means the size is also at most n over 2. That means this step also takes time at most n over 2. Okay, now when you put everything together, what do we have? The time for star is t of n over 2, and time for star star is also t of n over 2. And the maximum of this 2 clearly is just t of n over 2. Okay, that gives us that the final time complexity has the following relation, which is the constant times t of n over 2. Okay, so if you don't see the, let me actually carry over what we had before to see how we get this C1 plus C2 plus max time for star time for star star. So basically this is a case 1 if we go to left, or case 2. Okay, and we're taking the worst because we're looking at the worst case. And this is t of n over 2. Each of this is t of n over 2. As such, we have this is C1 plus C2 plus max, the larger of t of n over 2, t of n over 2. And the larger of this 2 is just t of n over 2. So we have C1 plus C2 plus t of n over 2. And that's what we have here. Okay, because so this is just constant. So I'm writing only a single constant here now. Okay, note that this recursive relation is when n is larger than 1. Once the size of the array becomes smaller than or equal to 1, what happens? Well, we got into the base case. This is our base case. And in the base case, we simply check a few the entries and we just return. So that's only take constant time. So this is our full recurrence relation of the time complexity of the algorithm. Okay. All right. Now, in general, okay, note that this gives us a relation of how the time complexity function relates to itself, but recursively, okay? But this does not yet give us the time complexity, okay? We don't exactly know we don't have a formula for T of n. We don't yet know precisely what is T of n, okay? We only know T of n satisfies this recurrence relation, okay? So what this means is that we now have to solve this recursive relation in order to obtain a non-recursive explicit formula for T of n. Okay, and that's what we do next. Okay, now in general, when we are given the recursive relation, recurrence relation, okay, note that recurrence relation actually happens very often in practice. Pretty much every time you write a recursive algorithm, naturally you get the recurrence relation because when you write out time complexity, the bigger time complexity depends on the time complexity of this algorithm on a smaller input. Okay, all right. So it's important to solve them. Now, one way to solve this is the following strategy. Okay, given this recurrence relation, you first unroll it a few times to see whether you can see any pattern. Okay, and once you see a pattern, you write out a general formula for the case unroll, and then you solve for the you ask that how many times do I have to keep unrolling this till I reach the termination case, the base case. Okay, because once you reach the base case, you don't have to unroll anymore. There's no recursive call anymore. Okay, so you need to solve the number of unrolls you needed, and then you plug in that number to help you to get the general formula. Okay, so again, let's look at the precise this example to get more details. Okay, so this is a recurrence formula we have. What do I mean by that? Step one. So let me just point, before I start, let me point out the termination in general, for any algorithm, in fact, as long as you have a termination, you can always assume that when the time is small for small constant, the time complexity is constant, okay? Because even if your algorithm is very slow, but if the input size is only constant, then no matter what you do to constant, that's still a constant, okay? All right, so in my unrolling, when I'm going to solve this recurrence, I'm also going to assume that n is a power of 2. This is just so that I don't have to worry n over 2 is not an integer, have to use either floor or the ceiling and so on. That okay, it doesn't change the time complex solving this recurrence. So in practice, when you do your homework, you can always assume that n is a power of 2 if that helps with analysis. Okay, all right. So step one, we unroll it a few times to see whether we see a pattern. What does that mean? Well, what it means is that note that this is a general formula. So I know that if I give you, so what is really this relation? This relation says that if I give you the problem of size star, then whatever the current size is, the time for that can be written as that if you solve it for size half of this, for the time for half of the size plus a constant, okay? So this can be, this is basically a variable. Okay, so for example, T8 will equal to T8 divided by 2, which is 4 plus this, and so on. Okay, so this is any number. Okay, all right. So now I look at this. This we don't like because I don't know what is this. Okay, but I do know, in fact, I just erased it. But I do know this relation holds for this problem as well, for this size as well, okay? In other words, even though I don't know what is T of n over 2, I can apply the same relation and then get to that T of n over 2 using this relation. That's T of n over 2 divided by 2. That is n over 4 plus C plus the original constant. In other words, I'm using the relation. I'm using this relation applied 1 star equal to n over 2. So this means that T of n over 2 equal to T of n over 2 divided by 2, that's n over 4. So I plug in this relation here. This is what I get, okay? If I write it out more better, I get n over 4 plus 2c. This is after one step of unrolling, okay? We look at this. Again, we don't like this because we don't know what that is. We still have to, again, I don't know what that is, but I can make it even smaller, okay? So now using the same relation to n over 4, we have that. Okay, so we plug in this here. That means that I'm simply replacing this using this. Okay, and if I take it out of the parentheses, now we have T of n over 8 plus 3 times C. Okay, so I can continue, but probably by now you already see a pattern. Okay, what is the pattern? Well, we notice that every time when so this is the first unrolling, And this is second unrolling. What we see is that every time you perform this unrolling, you expand it using this formula. Inside the variable, the size divided by 2, because every time we apply this, it's half the size, okay? And outside, I add one new additive factor, which is c, okay? So you can imagine that if I do this k minus 1 time, k times, k plus 1 time, what we have is actually every time inside it divided by 2, and outside you add another c. So after k times, you have k times c. So this is what we have. So in fact, we already come to the second. So this is the first step, finding the unrolling pattern. And then what we notice is that on the case unroll, we have this general formula, because every time, again, each time you unroll, inside you divide by a factor of 2. Outside, you only add another c, which means that the coefficient here increment by 1, okay? So as I do this k times, then I have the following: inside divided by k times. So if you divide 2 by k times, that's the same as divided by 2 to the k, okay? So this is, for example, this is 2 squared, and this is 2 third, okay? All right, when do we stop? We stop when we reach the base case, right? So in other words, if this already reaches the base case, then I don't have to do this unrolling anymore. And the base case is 1 inside becomes size 1, or in general, some constant. You can assume that any constant is okay. Okay, so we stop when this happens, because then when that happens, this becomes t of 1. I don't have to unroll anymore. Okay, so what does it mean? It means that 2 to the k, we stop when 2 to the k equal to n. That means that k equal to log n base 2. I should be careful here. Okay, so we stop when this happens. Okay, so that is the third step. Okay, same as what I wrote on the screen. Okay, now the last one is that we simply now plug in this to our formula. So what do we have? We stop when n divided over 2 to the k equal to 1. That means that inside it becomes t of 1, and outside is c times k, and this means k equal to log n base 2. And we said that the t of 1 is just a constant, because that's a base case, okay? When your problem size is constant, your time complexity is constant. So this means that the whole thing is big theta. The dominating factor is this logarithmic function here. So I can just write log n, okay? So that is the final time complexity, okay? Oops. And this is just to summarize what we have. So in the end, we get to that by doing this unrolling. So basically keep doing unrolling to get a general formula till we cannot unroll anymore. Okay, so you keep unroll this using the same recurrence relation till you cannot unroll it anymore. And then at that point, you figure out how many steps it takes and then plug in the value of k and then get the time complexity. Okay, so that's what we have for the time for the binary search. Okay. All right, just now remember that the linear search takes time n, and the binary search takes now, we just showed that it takes time log n, okay? So what's the difference between these two? Just to show you the contrast between, basically we're now talking about n versus log n. Okay, I just want to show you the contrast between these two. Log n is significantly smaller than n. Okay, so the algorithm, a log n algorithm is much faster than a linear time algorithm. Okay, just to get some idea, let's say that you have 10 to the 19th grain of sand, and you need to find they're already sorted. Okay, each one has a number. You need to find a particular grain. Okay, what does that mean? Okay, linear time algorithm means that, well, let's say that each basic operation takes 1 nanosecond. Linear time means that if I need to take 10 to the 19 nanoseconds, because I need n times. Okay, so n times, I need this much nanoseconds, and that's about 317 years. Okay, now what is the logarithm? So this is linear. What is log m? This is log, let's say that we use log 2m. This is log 2 10 to the 19, which is 19 log 210. Now, log 210 is actually roughly 3. Okay, so what this gives us is only 60 nanoseconds. So what we have is that if you do binary search, you only have 60 nanoseconds. Yet if you do linear search, this is 10 to the 19th nanoseconds, which is more than 300 years. So the difference is huge when your input size is large. Okay, so logarithmic is far more efficient than linear. Okay, that's why the sum sorting really help to improve the performance of the search, because now we can do binary search. Okay, well, but I do want to point out that to perform this binary search, you cannot run on any array. You have to run it on a sorted input array. Okay, so it does need a pre-processing. Okay, but as we pointed out, this is worthwhile when you are going to have many queries, which is particularly the case when you have databases or when you need to perform online queries efficiently. Okay, I mentioned at the beginning, in practice, databases are often indexed by certain keys, which may or may not be real values. Okay, and they may not exactly use the binary search we talk about, but usually they use variants of this idea. Okay, to search for specific elements. Okay, in practice, either that often the data structure they have is something called a B tree, which is more similar to later we're going to talk, instead of a sorted array, it's more like using a tree to represent the sorted array. Okay, we're going to talk about binary search tree later, which is closer to the B trees. Okay, and the reason for that is not because that it just array itself is not sufficient. It's because it's because that in practice you also have dynamic updates to your database. You may also want to insert and delete, in which array is not very good, and using trees as a more flexible data structure for that. Okay, we'll come to this point later in next week. Okay, all right. So